Level 0. Picture yourself standing in an open field at noon. The sun blazes overhead, a disk of light so bright you can't look directly at it. Around you, warmth seeps into your skin. Plants grow. The world thrives. For billions of years, this star has been the anchor of everything we know. And yet, in the cosmic hierarchy of stellar extremes, our sun is absolutely unremarkable. It's a star, yes, a sphere of hydrogen and helium about 865,000 miles across, where gravity crushes atoms together with such force they fuse, releasing energy that pushes back. In the most simple form, stars are mostly hydrogen and helium gas, and gravity crushes those atoms together, fusing them and releasing energy. That energy pushes back against gravity, and this balance is what makes the star give off light and remain alive. Our sun is what astronomers call a yellow dwarf, surface temperature hovering around 10,000 degrees Fahrenheit. It's been burning steadily for 4.6 billion years, and will continue for another 5 billion without much variation. No surprises, no drama, just reliable, predictable fusion. In the grand catalog of stellar phenomena, our sun is the default setting, the baseline, the cosmic return to factory settings option. But here's the thing about baselines. They only exist to be shattered. But what would make a star extreme? Well, this is where their size, mass, and temperature come in. Extreme stars will either be way smaller, larger, hotter, colder, denser, and way more compressed than regular stars like our sun. Every second, the sun converts 600 million tons of hydrogen into helium through nuclear fusion. This process releases enough energy to power human civilization for 500,000 years. Yet compared to what's coming next, this output is practically nothing. But what happens when you shrink a star down to barely larger than Jupiter, yet make it so violent it murders entire planets? Level 1. To understand what makes a star extreme, you need to picture a simple diagram. Temperature on the bottom, brightness on the left. Every star in the universe can be plotted somewhere on this chart, and their position tells you everything about how they live and how they'll die. Massive blue stars are right up here. They have short lives and burn themselves out in millions of years. Yellow stars like our sun sit in the middle, 10 billion years of mediocrity. Then way down here on the right, red dwarfs. Tiny, cool, and not the brightest. These stars seem insignificant at first glance. The runts of the stellar family barely scraping by with just enough mass to ignite fusion in their cores. But they hold a secret that makes them profoundly extreme. They live for trillions of years. That's way longer than even the age of the universe right now. They sip their hydrogen fuel so slowly that they'll still be burning long after every massive star has detonated and died. They should be the most boring stars in the universe. Except they're not, because being small makes them unstable and violent. They fire off solar flares hundreds of times stronger than our suns, enough to fry any planets unlucky enough to orbit them. A real example of a red dwarf like this is TRAPPIST-1. Compared to our sun, it's only 9% the mass, 12% its radius, and 0.05% of the sun's brightness. It's barely bigger than Jupiter. By every metric, it seems like a stellar failure. Yet this miniature star blasts out storms of radiation constantly, and surrounding it are 7 Earth-sized planets packed together, all of them literally closer to TRAPPIST-1 than Mercury is to the Sunday. Astronomers once thought some might be habitable, potential havens for alien life, until we realized that TRAPPIST-1 would literally roast those planets alive with its radiation. Imagine living on Earth, but every few days the sky explodes with star stuff that could strip away your atmosphere. That's TRAPPIST-1, a tiny star that murders entire planets. Hot plasma surges straight from the core to the surface, tangling magnetic fields that snap and release monster stellar flares. The magnetic chaos is so violent that any planet trying to maintain an atmosphere faces constant bombardment of charged particles and lethal radiation. But what about the extreme stars on the other side of the diagram? The massive blue stars? These are called O-types, and they can evolve into Wolf-Rayet stars, the most extreme stellar objects in terms of sheer output and violence. R136A1 is perhaps the most massive star ever discovered. This monster is up to 291 times the mass of our sun. It's also 9 million times brighter. Surface temperature, 53,000 degrees Fahrenheit. And its winds? They blow off the equivalent of Earth's mass every single month. This thing is literally shedding like a snake, peeling away its outer layers and hurling them into space at speeds exceeding 2 million miles per hour. The radiation pressure is so intense that the star can barely hold itself together. And the best part? Even with all the mass loss, it's still destined for the most violent end in the universe, a hypernova. See, when a massive star runs out of fuel, its core collapses, triggering a supernova, one of the biggest explosions in the universe. But what makes O-types and Wolf-Rayets interesting? Wolf-Rayets have a delicate balance. Not only do these stars have to rotate fast enough to shed their outer layers, but they also can't go too fast. Otherwise, they'll lose too much angular momentum. They also can't have too many metals, space language for anything that isn't hydrogen or helium. But in order for a hypernova gamma-ray burst event to happen, they have to originate from within the core. And as they tear through the star, they trigger explosive fusion, creating the element nickel-56, which makes them 10 times more powerful than a supernova. These gamma-ray bursts can be detected from billions of light-years away, beaming concentrated death across the cosmos. And that's the spectrum of stars. On one side, the tiniest stars live trillions of years. On the other hand, the most massive stars die in just 5 to 10 million years. Stars are the fundamental level of every extreme object, so much so that some of the most incredible objects in the universe are binary systems, two stars orbiting each other. In fact, up to 85% of star systems could be binaries. And when two massive stars orbit each other, it's violent. But what happens when you lock two of these monsters together and let them tear each other apart? Eta Carinae is one of the most extreme space objects ever discovered. It's 7,500 light-years away, made of not one but two giants. The first star is potentially up to 80 times the mass of the Sun. The second is potentially up to 100 times the Sun's mass. But that's only today. When it was born, it was perhaps up to 200 times the Sun's mass. How is that possible? The largest star is shedding itself because it's a variable star. That means it can radically change its brightness and size in violent explosive events. In 1843, the brightness from this larger star was so ridiculous that it became the second brightest star in the night sky for years. People in the southern hemisphere watched as this distant star suddenly blazed brighter than almost anything else in the heavens. And the smaller star that orbits it? It crashes through that same material, stirring the whole thing into the homunculus nebula, a twisted hourglass structure of ejected gas and dust. The collision creates shock waves that heat the gas to millions of degrees, producing X-rays we can detect from Earth. Both stars are building toward catastrophic deaths. When they finally explode, the blast will be visible from Earth in broad daylight. Now you're thinking, nebula? What does that even mean? But what happens when stars leave behind clouds so extreme they become colder than the void of space itself? Level 2. Nebulae are leftover hydrogen and helium gas from stars that have died. They push this gas back into the universe, forming beautiful clouds that glow in impossible colors, stretching for light-years across the void. In fact, this is where brand new stars will be born. And these clouds are home to some of the most extreme behaviors, like being the coldest place in the known universe. Most nebulae are warm, energized by nearby stars. They're stellar nurseries where new stars will eventually form, recycling the materials of the dead into the building blocks of the living. The Orion Nebula, the Eagle Nebula, all of them glow with the light of young stars being born. But some nebulae break the rules. An example of this is the Boomerang Nebula. It sits about 5,000 light-years away, and it's so cold it actually dips below the temperature of the universe itself. How? This nebula is formed by a dying star ejecting its outer layers at insane speeds, over 500,000 kilometers per hour. That rapid shedding causes the gas to cool through adiabatic cooling. Basically, it's the same way compressed air in a can feels cold when you spray it. The result? Temperature plunges to just 1 Kelvin. That's 272 degrees Celsius, only a fraction of a degree above absolute zero. The cosmic microwave background, the leftover glow from the Big Bang, sits at about 2.7 Kelvin. That's the baseline temperature of the universe. The Boomerang Nebula? Colder than the void between galaxies. That makes the Boomerang Nebula the coldest known natural place in the universe. If you could somehow survive inside it, you'd be experiencing temperatures lower than anywhere else in the natural cosmos. Only in laboratories on Earth have we achieved colder temperatures, and even then, only for fractions of a second. Nebulae teach us something fundamental. Stars don't just live and die, they reshape their surroundings. They leave scars that will eventually collapse to form new stars, new systems. But that's just level 2, gas from stars. Level 3? That is where extreme corpses come in, the dead bodies of the stars we just covered. But what happens when matter gets compressed so violently it stops being matter as we know it? Level 3. But before we talk about what makes these star corpses so extreme, we have to explain the 2 ways that stars can even die and become corpses. If the dying star is small, like our Sun, they puff up and leave behind a white dwarf. As the star ages, it swells into a red giant, sometimes growing large enough to swallow inner planets. Eventually, the outer layers drift away, leaving only the core. This is the leftover core of the star, made of degenerate electrons, which has the mass of the Sun and the size of the Earth. White dwarfs are compressed beyond normal limits. The atoms are crushed so tightly that electrons can't move. A teaspoon of white dwarf material would weigh about 5 tons. These objects don't burn, they don't fuse. They just sit there, radiating away their leftover heat for billions of years until they fade into cold, dark cinder. However, if the star is above 8 to 10 solar masses, they die through a supernova. What remains will either be a neutron star or a black hole. But what exactly are these two extreme objects? Firstly, the neutron star is a city-sized sphere of degenerate neutrons, made of matter so dense a teaspoon of it weighs billions of tons. While white dwarfs stop collapsing because electrons can't get closer, neutron stars take this a step further. The protons and electrons in the star actually smash together, creating neutrons, forming a solid ball of pure neutron nuclear matter with no empty space left at all. The surface gravity is 2 billion times stronger than Earth's. This process means we now call them degenerate neutrons, and they come in 3 variations. Regular fast-spinning one, magnetars that emit the most violent magnetic fields you could imagine, and pulsars that spin so fast and beam radiation visible from Earth. These rotate hundreds of times per second. The fastest one we've ever found? PSRJ 1748-2446 AD. It spins 716 times every second. At its equator, the surface is moving at 24% the speed of light. Magnetars have magnetic fields so intense they would pull the iron from your blood. Pulsars sweep beams of radiation across space like cosmic lighthouses, but neutron stars aren't the endpoint. The second extreme object from supernova outcomes are black holes. This is where the core has such strong mass and gravity when it collapses that it becomes a point, the singularity. A black hole isn't just a void. It has layers. The event horizon is the ultimate point of no return, where light simply cannot escape. Cross it, and you can never leave. Even though the singularity is infinitely small, with infinite density, yes, infinite. The event horizon size is called the Schwarzschild radius. Just inside that, you have the inner event horizon. Outside of these, a photon sphere where light bends, and an ergosphere where you can orbit the black hole and not immediately die. But what you see from Earth is not the event horizon. It's the shadow. Light goes on a roller coaster and you no longer can see anything. Some theories suggest black holes could have hair on their event horizon, tiny quantum fingerprints encoding information of what fell in. Oh, and by the way, black holes can rotate up to 95% the speed of light. The most extreme version confirmed? The 66 billion solar mass black hole behemoth known as TON 618. This beast is the center of its own galaxy, consuming billions of stars alive. The radiation outshines almost anything else in the universe. But what if the most extreme version isn't the biggest black hole, but the smallest? Meet the unicorn, the tiniest black hole candidate, just 3 times the mass of the Sun. Some scientists believe it's just a stripped-down star. It's just as rare as a unicorn. If the star that made this was even a tiny bit smaller, the unicorn would just be another neutron star. Instead, this little monster sits just 1,500 light-years away, and its event horizon is only about 18 kilometers wide, the length of Manhattan. But instead of skyscrapers, it's a singularity of death. Even the smallest black hole is still a point of infinite gravity and would still consume you and the Earth. And on that note, the real level of extreme objects begins when black holes feed. But what happens when they devour everything around them and light up brighter than 1 trillion suns? Level 4. If anything interacts with a black hole, they'll be shredded and swirled into an accretion disk, heating up to millions of degrees, blasting X-rays brighter than whole galaxies. Material spirals inward. As particles collide at near-light speed, friction heats them to millions of degrees. They glow, brighter than entire galaxies. When a black hole large enough gains an accretion disk, they ignite and light up the universe. That's what we call a quasar. Quasars are among the most luminous objects in the cosmos. Some are visible from billions of light-years away. TON 618 isn't just a massive black hole. It's a quasar, actively feeding, blasting radiation that outshines almost anything else we can observe. But did you know that there's something more extreme than that? The most extreme objects in the universe come in pairs quite often. 2 white dwarfs which go boom with a unique supernova, 2 neutron stars which go to kilonova, 2 black holes which absorb into each other. But there is even a quasar that has 2 supermassive black holes, both feeding, blasting 2 death beams of energy across the universe. Yes, a binary quasar. OJ 287 is a binary supermassive black hole system. The smaller one, 150 million solar masses, punches through an 18 billion solar mass black hole quasar accretion disk every 12 years like clockwork. And boom, the whole galaxy flares up brighter than 1 trillion suns. We've even studied this from Earth for 130 years. How? Because this extreme object is also known as a blazar. This is a quasar whose relativistic jets are pointed straight at Earth. And every time the smaller black hole goes through the accretion disk, we can detect violent flares shooting across billions of light years, radiation that left that system when Earth was a completely different world. The jets move at nearly the speed of light, carrying energy equivalent to millions of supernovae. When they're pointed at us, we see the full fury of a feeding supermassive black hole. All of this to show you that extreme space objects start from some of the smallest little stars and expand to the brightest and most violent beasts in the known universe. And at the core of everything extreme? Stars. From red dwarfs that live trillions of years but rage with constant violence, to massive blue giants that die in hypernovae, to the corpses they leave behind. White dwarfs, neutron stars, black holes, and finally to quasars that devour galaxies. Every extreme object traces back to the same fundamental forces, gravity and fusion, pushed beyond all reasonable limits. But we've only scratched the surface. In 2024, the James Webb Space Telescope detected something impossible, a galaxy that shouldn't exist. JADESGSZ 140, formed just 290 million years after the Big Bang, already containing billions of stars. The problem? There wasn't enough time in the universe for it to exist. Scientists are scrambling. Some suggest our models of galaxy formation are completely wrong. Others whisper about physics we haven't discovered yet. Dark matter? Dark energy? Or something else entirely? And then there are the signals. Fast radio bursts, repeating pulses from deep space, some lasting milliseconds. Others persisted for years. FRB 20220610A traveled 8 billion light-years to reach us, the most energetic burst ever recorded. We don't know what causes them. Somewhere out there, beyond the edge of what our telescopes can see, beyond the limits of our current physics, something is happening. Something extreme enough to make everything we've covered seem ordinary. The universe is only 13.8 billion years old, but it could exist for trillions more. What kind of extreme objects will form in that time? And what if some of them are already out there, waiting in the darkness, so extreme we don't even have the instruments to detect them yet?